You know, sometimes I look up at the night sky and it hits me that I'm not just seeing a bunch of lights. I'm
Ah.
I'm looking back in time.
You really are. Every single one of those stars is like a little time capsule from a different cosmic era.
Which is exactly why we wanted to do this deep dive.
Hmm.
We're going to get into how astronomers map that history using stellar populations.
Right, and it's a system that really got formalized back in 1944 by Walter Baade. He built on some earlier ideas, but he's the one who really pinned it down.
And the whole system hinges on two things: age, which makes sense, and this other thing called metallicity.
Yeah, we have to clarify that right away. When an astrophysicist says metal, we don't mean like iron or gold.
No.
We mean basically everything on the periodic table that isn't hydrogen or helium. So
Yeah.
oxygen, carbon, neon, all metals.
And the core rule is pretty simple, isn't it?
It is. The less metal a star has, the older it is. It's like a cosmic clock.
Okay, so if we're using that clock, where does our modern era, our stars, fit in? What's population I?
Population I, or Popeye, is us. It's
Yeah.
now. These are the youngest stars,
Yeah.
cosmically speaking, and they have the most metals because they've inherited them from countless generations of stars before them.
Our sun is one of those, right?
A perfect example. It's an intermediate Popeye star, and its mass is about, what, 1.4% metals.
And you find them right in our galactic neighborhood, in the spiral arms of the Milky Way. They're just kind of cruising along in these nice regular orbits.
Exactly.
But what I think is so cool is that the Kepler telescope data showed a link between this and planets.
Oh, a huge link.
The big gas giants, they seem to only form around these metal-rich Popeye stars.
It makes sense. You need that raw material to build big planets.
Yeah.
So if Popeye are the kids, then population 2 are kind of like the great-grandparents.
Older and therefore metal poor.
Much poorer. They formed way earlier in the universe's history. We find them in the galactic halo, the bulge, and inside those really ancient, beautiful globular clusters.
But even though they don't have a lot of metals overall, their chemical signature is really specific, right? It tells a story.
Absolutely. It's a huge clue. Pop-2 stars often have a higher ratio of what we call alpha elements, things like oxygen and neon compared to their ion content.
And that tells us what exactly?
It tells us they were born in an era when the only star factories running were these massive Type 2 supernovae. They were the ones seeding the early universe. We're literally reading the recipe of the first cosmic kitchens.
And trying to piece together that ancient recipe, I mean, that requires just immense amounts of data analysis. You have to find these tiny signals in the noise.
It's a monumental task.
Speaking of making sense of complex data, this deep dive is sponsored by Embersilk.
Uh-huh.
If you need help figuring out where AI agents could make the biggest difference for your business or even your personal life, check them out for AI training, automation, or software integration. That's embersilk.com.
So we've done the kids and the great-grandparents. Now we have to talk about the ancestors, the hypothetical ones, population 3.
Hypothetical, because we've never actually seen one.
Not for sure, no. These would have been the very first stars, formed from nothing but the material left over from the Big Bang,
So just hydrogen and helium?
and maybe a tiny, tiny bit of lithium.
Mm-hmm.
But that's it. No metals at all. We think they were enormous, incredibly bright, and lived very, very short lives.
But they were so important. They were the universe's first element factories.
They were everything. They cooked up the first 26 elements inside their cores, all the way up to iron. And when they exploded, and they exploded spectacularly, they seeded the cosmos with those new metals.
And that's what allowed population 2 stars to form in the first place.
Exactly. They also kind of flipped the switch on the whole universe.
Yeah.
Their intense radiation is what triggered the reionization period. Finding one is a huge goal for the James Webb Space Telescope.
And there was a recent report, right? Something called LAP-1b.
Yes, very exciting. It's still being studied, but it's the first system we've found that seems to be consistent with what we'd expect from a Pop-3 star. Still early days, though.
So you have this incredible timeline. Pop-3 makes the elements, Pop-3 uses them to build the early galaxy, and Pop-Thing is our home today. It's this beautiful story of cosmic recycling.
It is, which leaves you with a really fascinating thought to chew on.
Go on.
The model suggests that a really low-mass pop-through star, say, under 0.8 solar masses, could, theoretically, still be alive today.
If it got kicked out of its nursery before it could get polluted with more metals.
Precisely. So could one of the universe's very first stars be hiding out there, completely undetected, right here in our own Milky Way?
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.